Hello and welcome to Tvaritam AI. In this video, we are going to talk about normalization. Normalization in machine learning is the process of rescaling numerical features so that they fall within a similar range. In real-world dataset, different features often exist on different scale. For example, consider a dataset where one feature is age. Age usually ranges between 0 and 100. However, another feature in the same dataset such as salary or transaction amount may range from thousands to even millions. These large differences in scale can create problems for several machine learning algorithms, especially linear models such as linear regression and logistic regression, as well as neural networks. Normalization helps address this issue by bringing features to a comparable scale. There are several benefits to normalization. It brings all features to a similar scale. It prevents certain features from dominating the model. It often helps the model converge faster during training, and in many cases it can lead to more stable and better performing models. One important point to remember is that tree-based algorithms such as decision trees, random forest and XGBoost are generally insensitive to feature scaling. This is because they split data based on thresholds rather than distances, so normalization is usually not necessary for these tree-based models. Now moving forward with different type of normalization techniques, the first technique is max absolute scaling. In this method, each value of a feature is divided by the maximum absolute value of that feature. This scales all values into the range -1 to 1 while preserving the original sign of the data, meaning negative values remain negative and positive values remain positive. Another advantage is that it preserves the shape and distribution of the data. However, there is an important limitation. If the dataset contains very large outliers, the maximum value will become extremely large, and as a result, most other values will shrink close to zero. When we have data that lies within a fixed range, another technique is often used, which is min-max scaling. In min-max scaling, it rescales value to a fixed range between 0 and 1. It works by subtracting the minimum value from each observation and then dividing by the range, which is the difference between the maximum and the minimum values. So the formula is value minus minimum value divided by maximum minus minimum. The transformation ensures that the minimum value becomes 0, the maximum value becomes 1, and all other values lies between 0 and 1. Min-max scaling preserves the original shape of the distribution, which makes it useful when the data does not contain extreme outliers. However, the limitation of min-max scaling is that it is also very sensitive to outliers. If a single value in the dataset is extremely large, it will stretch the range and compress the rest of the data into a very small region. Another technique that is usually utilized is standardization or Z-score scaling. It rescales the data by subtracting the mean and dividing by the standard deviation. The transformation centers the data around mean equals to 0 and standard deviation equals to 1. In other words, each value represents how many standard deviation it lies away from the mean. Standardization works well when the feature distribution is approximately normal, meaning it resembles a bell curve, also known as a Gaussian distribution. In real-world dataset, the distribution may not be perfectly normal, but if it is roughly symmetric and close to normal, Z-score scaling is often an effective choice. However, Z-score scaling relies on the mean and standard deviation, which means that extreme outliers can still influence the signal processing. To make scaling more resistant to outliers, we use robust scaling. Robust scaling is specifically designed to handle dataset that contains significant outliers. Instead of using the mean and standard deviation, it uses statistics that are more resistant to extreme values. In robust scaling, we subtract the median from each value and divide by the interquartile range. The interquartile range is the difference between the third quartile and the first quartile. Q1 represents the 25th percentile and Q3 represents the 75th percentile. Since the median and IQ are focused on the central portion of the data, extreme outliers have much less influence on the scaling process. This makes robust scaling particularly useful for datasets where outliers are present but should not dominate the feature scaling. When it comes to values that are highly skewed, we use log transform. Log transform is used especially when there is a large difference in order of magnitude. For example, if a feature ranges from thousands to millions, the distribution may be heavily right skewed. Applying a logarithmic transformation compresses large values and reduces skewness, making the distribution more balanced and easier for the model to learn. Custom scaling is also an option that we provide. We may want to define our own scaling approach based on domain knowledge, and that is where custom scaling can help you. We define a centering parameter and a scaling parameter, and the transformed value become value minus the centering parameter divided by the scaling parameter. This approach is useful when domain knowledge suggests that a feature should be normalized in a specific way. Now moving forward with the implementation, you see in the normalization pane I have different features. First feature is age. Now age is close to a normal distribution. It is not a perfectly normal distribution, but because it is slightly closer to a normal distribution, I can go with z-score scaling. So I just need to select the normalization technique and click on apply, and it is automatically applied. Second is temperature. Temperature is close to a uniform distribution. Again, it is not a perfectly uniform distribution, but it is close to a uniform distribution, and I can go with a min-max scaling, as also you can see there are not a lot of outliers. So we go with min-max. Now comes income. Income here has a lot of outliers. So I can also go with robust scaling. But here in income, it is not only the outliers that are there, but the magnitude, the order of magnitude is very different from thousands to millions. And as discussed, in such case, log scaling can help us to make extreme values less effective or make it less skewed. So what we can do, we can apply log scaling here. Now comes transaction amount. Transaction amount, the order of magnitude is not as big as there was in the previous one, but here also there are a lot of outliers. So what we can do, we can go with robust scaling. Then we have credit score. Credit score is close to normal. So I can also go with z-score scaling, but because credit score is usually bounded within a certain range, mostly 300 to 900 is the theoretical possibilities. So we can also go with a max absolute scaling in this case. All the scaling that you apply here is automatically applied during prediction, ensuring that the model receives inputs in the same scaled format when you are running the prediction. And the choice of normalization technique that you want to apply can depend on several factors. It can depend on the distribution of the feature, the presence of outliers, range and magnitude of the values also. So to understand the characteristic of the data, you need to make sure that you understand the distribution, outliers and the range and magnitude, and this can help you decide the most appropriate scaling method for each feature. Thank you.